You know. I want to go back, but no. Yeah. Okay, well, I guess I'll just skip the first slide. So, wait.
Oh, this is your slide.
Yes, this is one.
Okay, so can I use this other one to go back?
Yeah.
Yeah. Okay. So yeah, sorry for the technical trouble. Yeah, I'm going to be talking about a bit of a smaller question than Roi was talking about how we can understand where the sun was born, and I'm also going to be talking about some smaller scales than Roi was talking about. And yeah, very specifically, I'm basically going to go into detail in what's actually happening here when Roi talked about the gas turning into stars, and then the stars sort of going supernova and putting energy back into the gas. And yeah, I'm also using simulations of that, also of gas, but they're a bit different from those of Roi's. So this is, I'm kind of starting from where Roi kind of ended with these little balls of gas, although these are still 100,000 times smaller than those that Roi was talking about. So this little ball of gas is just a few tens of light years in diameter, and it is about 10,000 times as massive as the sun. But then we are going to be able to get into a lot more detail than Roi does. So yeah, this is just a little ball of gas. It's a bit idealized, but it's just easy to work with, and it's not going to be entirely like smooth and sort of even, because there's a little bit of turbulence being driven. So the gas is sort of being stirred. Although currently it's all standing still, so it hasn't really started yet. But as I start the movie, it's going to be stirred through, and there's going to be structures forming as it also collapses. I'm also using a little bit of a different kind of technique to model the gas than Roi was doing. So I don't think you can see too much from the back, but actually I'm using a grid method. So I basically have a whole bunch of little cells where we know how much gas there is, how hot that gas is. That's just a different way of doing it. Both have advantages and disadvantages. But yeah, it's mostly if you're very close, you can kind of see the grid, but I think it's too far, unfortunately. Okay, so let's just get it started. I think so you see some little structures forming, some little denser spots, and as it goes, I also kind of see these filaments forming, as was also happening in Roi simulation, because it's basically the same physics. It's all gravity, except that in my case there is no dark matter. Or, well, there is dark matter, but it's basically all throughout, and it doesn't really affect anything. So yeah, in the end it looks something like this. And at this moment, in some of these filaments, the gas is dense enough to start forming stars. And how does that go? Well, this is actually an observation where they took apart. Yeah, they looked at a part of the sky. The background is kind of like a normal telescope observation with some stars, but kind of overlaid is an observation of a filament of gas and dust in the infrared. And along this filament there are these little like denser spots, a little bit like beads on a string, where this filament is kind of fragmented into little bits. And that's going to be where the stars are going to be forming. So yeah, you start with kind of this, again, a little sphere of gas, which is going to collapse from the outside in. And then at the core, it keeps getting denser and denser, and at some point the heat cannot escape anymore, so it also gets hotter and hotter and denser, until it's hot enough to start nuclear fusion, and the star is born. So yeah, nuclear fusion is basically the mirror image of nuclear fission, which is how most of our nuclear reactors work, where you basically start with a very big atom, like uranium, and you shoot something at it, and it breaks apart, and you get a lot of energy. Now, in principle, you could try doing that again. Shoot something at the remainders, and try to get energy from that. And yeah, for these, you could actually get energy that way. But that doesn't work like going all the way down, all the way to like the very smallest bits of an atom. Because at some point it's going to cost you energy to actually split something. But then on the reverse, then it's actually going to gain you energy to fuse them, to make bigger components. So that's nuclear fusion. So you start with very small atoms and you squish them together and you get bigger atoms and a whole bunch of energy. And well, because the universe kind of started in the simplest way, so it started with a whole bunch of these very simple small atoms. So yeah, that's what these newly born stars will mostly consist of. So they'll be able to do this for a whole while they have a lot of this very simple hydrogen gas. Now, the stars you form then, there's quite a big range of them. It's mostly like divided along how big and massive they are. You have stars like the sun, which are a bit yellowish. There are some stars that are a lot bigger, for example 10 times the mass of the sun, or even more massive, which are a bit bluer, and less massive stars. For example, only 10% of the mass of the sun, which will be kind of reddish. And an interesting thing here, is that is also what also Roi said, was that these bigger structures will tend to be rarer. There are way more of these very small stars than these large stars. And also an interesting thing is that this process of nuclear fusion becomes way more efficient the more massive your star becomes. Because not only you have like a larger center where it's hot enough to actually do fusion, but all of the gas sort of outside is pressing on it even harder. So if you go 10 times in mass, you don't go 10 times in sort of energy production. And in fact, if you go from like 0.10% to the sun, you get 1,000 times more bright. Whereas if you go from the sun to 10 times the sun, you become 10,000 times more bright. And well, all of that energy that's being produced by all of these young stars is going to have an effect on the gas that is still surrounding it, that hasn't yet been incorporated into stars. So let's say you're, for example, on the beach or have gone swimming, and you want to go dry off. Then it's best to go lie in the sun instead of in the shadow. So the heat of the sun, the radiation of the sun, is going to warm the sort of water that's still in your skin, and you're going to dry off more quickly. Now imagine suddenly the sun is 10,000 times more warm, and maybe even the entire pool might evaporate. And kind of the same thing is happening with this gas that's still around. So here, this is a picture of the Orion Nebula, where about 1 million years ago a whole bunch of stars have formed, and all of those stars are still illuminating and blowing out the gas around it. So yeah, you see a whole bunch of stars here, and also the gas that has some very nice colors. And actually, if you kind of try to figure out how all of this gas is moving, you'll see that actually most of the gas is in sort of this sphere or shell like over here, and it's actually moving outward. So there are some stars over here that are very hot, very massive, and they're all blowing out this gas outwards. And in that way, kind of stopping the formation of new stars, until in the end you're just left with a star cluster, just a collection of stars without any gas that's just going to make its way through a galaxy, and in the end also going to kind of fall apart, but that takes way longer. Okay, now to take a little, and then also make to tie back into again what Roi was talking about, the supernovae. So we have on the one hand the nuclear fusion that could give you energy by fusing atoms, and on the other hand fission that could give you energy by splitting them. But there is kind of this center point where kind of none of those is happening, where where kind of a point where trying to fuse it would cost you energy and trying to split it would cost you energy. And that's actually at iron. So what the star is doing, it's going to fuse all of its hydrogen into helium. And then once that's gone, it can fuse all of its helium into carbon and oxygen. And then on and on and on, until it fuses everything into iron. And then it can't fuse it anymore. And then just the entire energy production of the star basically fails. And that energy production was actually the thing that had been sort of holding back this collapse that had been going on basically since the start of time. And yeah, this entire star implodes. And again, a part of that energy then sort of bounces back, and that's what we see as a supernova. Although, yeah, the majority of that energy and that mass kind of stays in a very dense, very small thing in the center. But yeah, this only happens like a few million years after the stars have formed. By that time, for example, the Orion Nebula will probably have ejected all of the gas directly around itself. But these supernovae are way more powerful, so they basically also affect regions way beyond, would affect like way beyond the Orion Nebula itself. So yeah, that's why these are more important on like the large scales than the radiation was on like the smaller scales. Okay, now to step back a little bit, how do then planets actually form? Because we've now seen how stars are born. So if you go back to this picture where we have this little core of gas that's been collapsing into a star, this thing is actually not just sort of statically ever collapsing in itself, but it also rotates slightly. And as it collapses and rotates, it rotates faster and faster. And you can try this if you're a skater and you try it like a pirouette, and then you sort of tuck in your leg, you actually go faster. So even if this very large core rotates only slightly, as it collapses, it starts to spin up. And then not all of the material that's collapsing is going to end up really on the star itself, but a part is going to kind of settle into a disk around that thing, which will be called a protoplanetary disk, because that's where the planets are going to form. So this thing can exist for quite a long time, a few million years. Yeah, and that's where planets are going to form. In kind of the gas that we've been following, there's also a little bit of dust, which are like little grains of sand or little bits of ash. They're maybe just a few micrometers in size. And as we kind of get into this protoplanetary disk, it actually becomes dense enough that they can sort of meet each other and stick together and grow into larger and larger particles. And eventually get into objects basically like the asteroid belt. These are some of the largest planetesimals in the asteroid belt, like dwarf planet Ceres and Vesta and Pallas. These are like tens, hundreds, maybe 1,000 kilometers in size. And then as these can then again collide, and as we also saw in the quiz, kind of these young planets can collide and maybe form moons or just stick in general and form larger planets. And then as they become even more massive, they can also sort of start to attract the gas itself and keep that to its surface, but they need to be quite massive for that, and then grow into gas giants like Jupiter. But yeah, that's kind of a picture where we only really look at what's happening in this protoplanetary disk itself. And also if you look at this thing, it doesn't really look like there's really much like going on from outside. But as we saw, at least in some like places where stars are being born, we have these very massive stars that are drive out this gas. And can they also drive out the gas around these protoplanetary disks? And the answer is yes. If you have those massive stars, you can actually do that. So again, going back to the Orion Nebula, if you really zoom in on this picture, you kind of see shapes like this, and I'll just enlarge one of those. So what you're seeing is a little star in the center, with a little dark shape around it, which is this protoplanetary disk. And then around that, there's this kind of cocoon of material. And actually, this is pointing away from one of the most massive stars, which is basically over there. And the radiation from that massive star is sort of irradiating the protoplanetary disk. It's evaporating this material around it, and that's just being blown away kind of downward. And yeah, that material, of course, is material that we will not be able to include in our planets. So if this happens fast enough, early enough, we might, extreme enough, we might not get, for example, gas giants. And it's not just gas that they can kind of strip away. If there's like still small enough dust in it, that dust might also sort of be blown away. So kind of like maybe a sandstorm, if you have like a very strong wind, you can like maybe like whip up some of the little sand particles. But yeah, for example, the larger boulders or like houses, they will just stay where they are. But yeah, still also that small dust that is being sort of blown away is also dust that will not be able to form the planetesimals and finally the planets. So yeah, so then of course there's the question, what does this mean for the solar system? Have these things happened to our own solar system? And well, I'm afraid to have to say we don't really know. All of this research is still basically too new to really have a final answer. Although kind of my intuition is that the solar system is like big and large enough. We have 4 gas giants with a lot of gas. We have 4 more planets. We have all kinds of dwarf planets. That at least there won't have been like too big in effect. Maybe at some point there was some strong irradiation, but maybe like we already had like some of the planets or some bases of the planets. But yeah, we probably hadn't been like really very close to one of those massive stars. So now I do admit that it's a bit maybe disappointing that I don't really have like an answer to give from what I've been working on. But there is actually an answer that can be given from like a different way, which is from meteorites. So if you study certain types of meteorites, you can find these what are called chondrules, which are basically these little spherical kind of molten bits of stone, kind of like marbles, which are really like the leftovers from the formation of the solar system. Basically, since the sun and the solar system were born, they've basically been this way. So if you cut them open and you see what's inside, you can really see, okay, what material was the solar system formed from? And one really interesting thing is that it appears that the solar system was formed from certain radioactive atoms, which would they're radioactive, so they would disappear relatively quickly. So there must have been something near the solar system that created these. And it's a little bit unlikely that, so one of the sources could be a supernova. But again, a supernova, it takes a few million years before that happens, and within a few million years, like a star that would go supernova would basically blow away your entire protoplanetary disk. But maybe like a supernova happens a bit farther away, or like other massive stars, like a different wave blowing this radioactive matter kind of into its surroundings. And then kind of from that material, sort of the sun was formed. So from this, it seems kind of likely that the sun did form in, at least not too far from where these very massive stars were born, and not in a very sort of distant part of the galaxy. but in kind of one of the more busy parts. So yeah, that's the answer that I have for you about what we know about where the sun was born. And yeah, we still have a lot to do to actually really figure it out from like the root of land formation. But hopefully we'll be able to figure that out in the future.
So are there any questions for Maite? Please don't be scared to ask. Yes.
I'm curious about your intergalactic dust. I don't know if that's the right term. Chemically, do you know what it is?
Yeah, it's mostly silicon and carbon that are basically form like the backbone. So in some cases there's also like ices sort of formed on it. So for example, water ice. If it's cold enough, if there's like little enough radiation, carbon monoxides can sort of form ices on it. Yeah, there's also probably little bits of metal. So yeah, most of the things that we know probably as solids here, they have like little bits in those interstellar dust grains. But yeah, mostly silicon and carbon.
And in terms of size, how many atoms would be in a lump? A grain?
Yeah, so one of those dust grains is about the question was how many atoms are in one of those interstellar dust grains. So yeah, I think an atom is about a nanometer in size, and these dust grains are about a micrometer in size. So yeah, depending on like if it's like really a chunk or if it's more of a fluffy thing, it's probably like 1 million to 1 billion atoms. I would estimate.
Thank you.
Yes, they're on the back.
Just for the meteorite, so you saw radioactive element in the meteorite, and then you can didn't it decay into iron as you were saying?
Sorry?
Did you see radioactive element in the meteorite?
Yeah. So the most important ones, why we sort of know that happened. Those have basically all decayed already, but we know very well like what they would have decayed into. So if what they would have decayed into is like more kind of is present more than what we would expect from like a normal mixture, then we know it was there previously.
Yes.
When you were showing the supernova and how the elements form, you went up to iron. How do the heavier elements form, and or where?
Yeah, so mostly in massive stars. So for example, in supernovas, for example, where you have this entire outer layers of the star kind of crashing down. That's an environment where you can get a whole bunch of interesting nuclear fusion and create a whole bunch of other heavier elements. So yeah, it's from supernovae. It's from some other things where like really exotic things are kind of colliding. So one thing that can be left over from a supernova is what's called a neutron star, which is basically like a very, very big, maybe 10 kilometer sized atom. And if you smush two of those together, you also can create a whole bunch of different interesting chemical elements.
Maybe one last question. Okay. Then let's thank Maite again. Okay, so now to finish the event, we are loading. We're going to thank the speakers again, and for that we want to give them this I guess, iced tea glass. Okay, so if Roi and Maite can come here, and then let's do another round of applause for the speakers. So we want to thank our team of Astronomy on Tap who have worked extremely hard these past months to find a new location, for a new venue for Astronomy on Tap to continue giving talks to all of you. And we'll see all of you again. Loading, well, next month, last Monday of the month, I think it's the 26th of March.
It's coming.
Yeah. We'll see all of you at the same location. It's going to be loading until tomorrow, so it's March 25th.
Okay.
So yes, I hope to see all of you for a new set of speakers.